Welcome to screencast session, week number 5, minimum cost spanning trees. To do the minimum cost spanning trees, we have two algorithms, Prim's and Critical. First, we are implementing the Prim's. The Prim's algorithm, as you know that it is taking the adjacency list as a parameter. So we are doing that basic initialization of all required variables. So let's do that. As usual, we are doing the calculation of this infinite. We have already available constant available in Python, that is INF. So once it is done, we try to do that some dictionaries and some lists of that. The widgeted dictionary and a distance dictionary. So we are doing a TE, which is the tree edges, so which is going to be a list. So it contains that one dictionary and the second dictionary, and we have that another one is list. So these three are initialized, but it is initializing that all of them, the dictionaries and the particular list of them are initialized with some value. So for that, we need one iteration for V inside your W list of keys, and whatever each particular visited value is there, that we are fixing, and as well as that visited of V we are fixing a value, and distance we are fixing a value for that. So these are two values. The first value is false because it's not visited, and the second value is going to be infinite. So once these two are fixed, so let's update that the start vertex is always started from 0. For that, the start vertex, so visited of the 0, it started with true, because always we start with traversing of minimum cost spanning tree always from 0th vertex. For so V and D, that's each vertex and distance we are getting. So from this W list, so what exactly it is, whatever 0th vertex is there, that 0th vertex, all adjacents we are getting, each adjacent we are getting it V. That distance we are updating. The distance of V is updated with D. So that from the 0, what is the distance to the V? So we got it, and that's updated. Now let's repeat the process n minus 1 times. N minus 1 is nothing but number of vertices. For this, we are using one for loop, that's I in range of, so I in range of 1 to, so that length of, so W list of keys, so how many number of vertices are there, that number of times it's repeated. So now in this, we try to do that updating of minimum distance. So basic minimum distance we are updating is infinite, because we don't know when it will reach. So what could be the distance? And next to widgeting vertex also we don't know, so that we are updating as none, so which is unknown next vertex what we are trying to update. Now inside we are trying to find out that next U to V edge, so where the UV edge is nothing but U is widgeted, V is unwidgeted. So for that we required one iteration outer loop of U inside your W list of keys. So W list of keys. So in this each U, we are trying to find out the respect to V. So in this particular V and D also distance all we are getting in. So W list of whatever U, from the U, what are the different adjacencies are available, that's called V. Here the most condition we are checking is, we try to do that you should be visited and you should be you should be visited of the U and not visited of V. So that means the root of the particular V is visited, but V is not visited. So and existing distance, if it is greater than the min distance, definitely it's true, because min distance is right now it's infinite. So now the min distance is updated with the distance. So the next visiting vertex also we are updating, that's going to be V, and traversing edge also we are getting the next edges, that is U to V. So U to V. So this we got it. These are next V is updated, and as well as that next edge also it is updated. Now what we do is, so mark that next V as widgeted. That's what we do. For that there is one more initializing, or we can say that updating, we can say that. So widgeted of that next V is done. So that next V, it will become, it's a true, and as well as whatever that edge is widgeted, that tuple value we want to append into that tree edges. The T is nothing but tree edges. So that is a next E. So that next t is nothing but tuple value. You can see that this is the tuple value. That tuple value we are appending. So once done, so we try to update that unvisited adjacent distances. So for that, so again v and t we are taking. So w list of next v, whatever the next v is available, that distances we are updating. That distances we are updating up from the next v. So the next v to v, what exactly is? If not visited of v, when it is not visited, so at this time, and we check it that the existing distance, if it is less than the distance of v, we try to update the distance of v is the smaller value of d. So this is updating, and as well as appending of t is done. So there might be outermost loop, yeah, all done. Finally, what do you return is the tree edges we are returning, whatever that minimum cost spanning tree is framed by including which edges. So this is okay. I think we entered into the Python compiler. Let's come out that. So we are taking the same particular tree which you have used in this GitHub notes. You can see that it's a graph. So graph is a fully connected one, but we want to create a minimum cost spanning tree. So the spanning tree is a connected one, but it's not fully connected. There is no cycle. So let's run this one. Yeah, hope you got it. So now you can observe it. There is a simple investigation. So whenever including edge, it should be the minimum. From 0, there are 2 edges are available. So 1 is there, 3 is there. We try to include the minimum. So 0 to 1 is included, 10. Then 1 to 3 is included because the distance is 6. So that's going to be 16. So then after it, so 1 to 2 is included. It's a 20 because it's a minimum one. Because 3 to 4 it cannot be because it's a 70 length. So now 2 to 8 is included. Sorry, 2 to 4 is included. That's a distance is 8. So including 10, 6 is 16, and then 20 it's a 36, 36 and 8 it's a 44. So excluding that largest distance of edges, like 18 is excluded, 70 is included, 70 is excluded. So hope you got it. So thank you very much. Have a nice day.